Hello, in this video we're going to talk about the half-life of first-order reactions and the applications of this to radioactive decay and carbon-14 dating. So what is half-life? So this is defined as the time for the concentration of a reactant to decrease to half of what it was. If you had 6, now you have 3. And then another half-life after that, you go from 3, now you have 1.5. So that's a half-life. You can write it out as it's the concentration of A at some time is equal to half of the concentration of A at time point 0. And so we can work with half-lives by using our integrated rate laws, which tell us how the concentration changes with time, and this little relationship that concentration at some time is half of original. All right, so let's do that. So here's the integrated rate law. And let's rearrange it to make life a little nicer. Plug in this, so we're saying that the concentration of A at some time divided by the concentration of A at some time divided by 2, right? So effectively these can cancel out, and then you just have 1 over 2, which becomes 2. So then the next step of this, all right, so this is just replaced with the natural log of 2, and then, okay, divided by k, natural log of 2 divided by k is equal to the half-life. And we just call this time as time 1/2, because it's the time it takes to, reduce and turn into half of what you started with. All right, natural log of 2 is 0.693. Keep in mind this 2 is exact because it came from half, the definition of a half-life, and so it doesn't affect your sig figs. Now, the cool thing here is for first-order reactions, the half-life depends only on the rate law constant and not on the concentration, which kind of makes sense. It doesn't really matter how much you have, this is the time for you to have half of it. Okay. Now, you can look at this kind of picture to try to get a better sense of half-lives. So you have some concentration. Sure, we'll start with 1 molar to make life easy. You go out 1 half-life, which is on the x-axis, the 1, and you have half of it left. You go another half-life, you have 0.25. You go another half-life, you have 0.125. And as you go more and more half-lives, the amount of change in concentration gets smaller and smaller and smaller. And that's okay, because we said previously that the rate of a reaction will change as the reaction proceeds, and so that's exactly what's happening here. All right, so one of the most common times when we talk about half-lives is when we're talking about radioactive decay. So this is what nuclei do that release radioactivity. They decay and transform into perhaps more stable nuclei by emitting small particles. And so just traditionally we talk about this with half-life and not rate constants. It's a first-order process, so we can use either one. It's just nicer to say, oh, the half-life is 5,700 years, as opposed to giving people the rate constant. Oh, the rate constant is blah, 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 blah. It's a lot more easy to understand when you talk about it in terms of half-lives and not anything else. So while we're here, this isn't so much pertinent to what we're doing, but what the heck is radioactive decay? I don't want to leave you hanging, so I'll tell you this. So there's several types of radioactive decay. Here's the 3 most common kinds. So commonly, an unstable particle will release an alpha particle. And an alpha particle is in effect a helium nucleus. So in this case, americium, which is in your smoke detectors actually, releases alpha particles as it decays, and then it turns into neptunium, 2 spots to the left on the periodic table. All right, beta decay is when a particle is emitted that's a beta particle. And a beta particle is in effect a fancy name for an electron. So in the process of emitting an electron from the nucleus, of all places, it turns a neutron into a proton. And then that changes what element you have. Then gamma decay is just high energy radiation. And usually this is paired with the release of some other type of particle, but not always. And so why are they called alpha, beta, and gamma? It's because scientists discovered alpha decay first, beta decay second, gamma decay third. In the Greek alphabet, alpha, beta, and gamma are the first 3 letters. That's simple. All right, so now let's do an example here. So strontium-90 is a byproduct of atomic bomb explosions. So while we're talking about the bomb, let's see what this is. So you have uranium. That's the material that's typically in kind of simple atomic bombs. And this represents a neutron. And so if a neutron hits this nucleus with enough energy, it will cause this nucleus to split. This is called fission, splitting. And then it'll split into a wide variety of different isotopes. A majority of it is strontium-90, but you can get all kinds of other isotopes as well that come out of this. And then critically, this releases 3 new neutrons, which then go on to then degrade more uranium nuclei. And so if you put too much uranium together, past the critical mass it's called, the number of neutrons coming off of it are enough to start an uncontrolled chain reaction, which kind of snowballs in a way. It gets bigger and bigger and bigger, releases so much heat, and explodes. Okay, again, not so much pertinent to what we're doing, but hey, it's kind of interesting to know. So, all right, we want to find the first order rate constant for the nuclear decay of this strontium-90. And so you can figure this out from the half-life. We have this equation that relates rate constant and half-life, and basically just plug numbers in. Solve this for K, plug the stuff in. Remember, natural log of 2 is exact, so that doesn't affect your sig figs. So then you have 0.0247 years. All right. So then, next step, the number of years required for 99% of this material to degrade, to disappear and turn into something else. So, all right, if you have degraded 99% of it, then there's 1% left. So this ratio of the amount of material at some time divided by the original amount of material is 1% over 100, or 0.01 over 1, or effectively just 0.01. That's 1%. So we have the first order integrated rate law. And one of the cool things about how this is phrased, right, is this here is just a ratio. So it doesn't matter what you put in here, right? Often we put molarity over molarity. Great. Well, if these are in the same container, moles over liters, you can cancel out the liters. So this is the same as, you can just say moles over moles. Well, if you use Avogadro's number, you can get number of atoms over number of atoms. If you use the molar mass, you can get grams over grams total. Like, whatever you have, as long as it's in this ratio, it'll still work and still be valid to use in this equation. So it's just kind of a nifty byproduct of this having a fraction in it of n at some time versus n initially. All right, so here we plug in our kind of ratios. We go from 1 to 0.01. And then I just noticed that I should have said 1.00 right here to make the sig figs happy. Ultimately, this isn't going to affect what we do, but hey, it should be 1.00. All right, so then now here's this, and we're basically going to solve for t. So here's the outcome of natural log of 0.01 divided by 1. Now 0.010 has 2 sig figs in it, and so we're going to have 2 decimal places in negative 4.60. So there's 2 decimal places there. So it doesn't matter if it's 1.0 or 1.00, the mistake I made here. And then, great, so there's that number. We have our rate constant. Now we're going to solve for t, and that's 187 years with 3 sig figs. Great. Now, what types of things can we do with this half-life? And probably the most important application of this is called radiocarbon dating. So carbon-14 is an unstable nucleus of carbon that has a half-life of 5,730 years. So how does this play into radiocarbon dating? So the idea here is that cosmic rays are continually bombarding our atmosphere, and they'll take nitrogen-14 and kind of facilitate the absorption of a neutron into the nucleus, which then kicks out a proton, and then moves atomic number 7 down to atomic number 6, turning nitrogen into carbon. Okay, these carbon atoms work their way into carbon dioxide, and then there's roughly a constant concentration of this carbon dioxide in the atmosphere, or of carbon-14 in the atmosphere, because as some of it decays, the cosmic rays form more of it, and it's kind of a just equilibrium state. Now, organisms on Earth will imbibe this carbon dioxide in some way, and so in all of our bodies, there's a roughly constant concentration of carbon-14. However, once we die, we stop taking in new carbon, and then the carbon-14 that's in our bodies decays slowly. And so, so say you have some tree, and then you cut it down and make paper out of it. How old is this paper? You can tell by finding how much carbon-14 is left in there. So somehow you measure the ratio of carbon-14 to carbon-12. You can do this by looking at how fast it's disintegrating, like how many releases of a beta particle you have per minute, per se, or time. And this can detect age up to about 40,000 years. Eventually, so much of this has decayed that it's really hard to measure how much carbon-14 is left, and that's kind of our upper limit of time that you can detect with this. But don't worry, scientists have other methods to work on that are under similar principles to figure out age of other things that are older. So, all right, so say you find in a cave by the Dead Sea some scrolls, and they have biblical writing on them, and you wonder, hey, are these real? So you can use this to figure out how old the scrolls are. So, because again, you chop down the tree, it stops taking a new carbon-14, and then that carbon-14 decays. So here's the half-life of carbon-14. First, we need to find the rate constant, which granted, once you do this once, then you know it, because, right, you're just dealing with carbon-14, which will have the same rate constant of 1.21 times 10 to the negative fourth inverse years. All right, we'll use that number in a minute. Second, let's find the time. So we're going to use the integrated rate law here. We're also going to use the fact that at our time now, the number of particles, number of carbon-14 nuclei, is 0.770 of what we started with, which is plants living today, right? So when this plant was alive, it had 1. Now it's decayed to 0.77. So here's the equation for the first order integrated rate law. We've already plugged in the K that we found on the last slide. And then let's plug the rest of the stuff in. We can take the relationship between N0 and NT and plug it into here. And then really these cancel out, so we're left with just the natural log of 0.770. These 3 are significant, which means we'll have 3 significant decimal places in our result after taking the natural log. And then that's equal to negative KT. Perfect, now we just got to solve. And the time here, since the organism died, is 2,156.5 years, or accounting for sig figs, 2160 years, basically. So, hey, the paper that these are written on is actually from biblical times, and then that can tell you something about the authenticity of the document. All right, so before we finish, I should point out the version of this that your book does to talk about radioactive decay. And it's a little more like real-world specific, because instead of talking about some ratio, it just gives you the disintegration rate, which is how you measure things. So let's get to what your book does. So first order integrated rate law on the left. Let's plug in the half-life equation in here. All right, that's all well and good. Now solve it for T, since ultimately we care about how long it's been since the organism died. Now into this ratio of concentration initially over concentration at some time, we can use the fact that, well, a ratio of concentrations is the same as a ratio of number of particles, which in the case of carbon-14 is the same as a ratio of disintegration rates. So the amount of decay, like the rate of decay, depends on how much of it there is. And then, of course, this is rate of decay per gram, because, you want to account for the amount of material you have. And so, all right, you and I have 15.3 disintegrations per minute per gram in our body. And then you compare that disintegration rate with whatever object you have. And so you basically just put a Geiger counter up to it, and it measures how many beta particles come off, and then you can use that number. And so here they use R for this, for rate, which is kind of an unfortunate variable to use because we use R for so many other things, but hey, whatever. And so you can just plug this in here. Now, one other thing is we know what the half-life divided by 0.693 is, and so we just plug this in here to make a nice, pretty packaged equation. And so when you're doing problems in the book, you basically just find what R is, and you plug it in right down here, and then you get your time out. Pretty straightforward, right? So I don't typically use this because really our goal for calculating stuff relating to half-life is to teach you about how to do these calculations. And this just makes it way too easy for this typical problem, and it's a little arbitrary, right? So I don't typically teach it this way, but I mean, it's a valid way to do it, and it's the way your book does it, so that when you do the suggested homework problems, this is what you're going to see. All right, that's all I have for this video. Thanks for watching.